So one of the problems that we work on in my laboratory is trying to understand the chemistry of chiral molecules when they're adsorbed on chiral surfaces. So chirality is actually a geometric property of objects, including molecules, and it's the geometric property that renders one structure non-superimposable on its mirror image. And the easiest way to think about this is the pair of hands. Everybody's familiar. The left and right hands are clearly mirror images of one another, but they're not superimposable. There's nothing that you can do to map one onto the other. Whereas, by contrast, if I took baseballs, the baseball is a mirror image of itself, and you can't tell the difference between the left and the right-handed baseball because there is no difference. So this matters a lot when you come to think about molecules that are complicated in their structures. So, for example, pharmaceuticals are fairly complicated compounds. They have structures that, if you take the mirror images are not superimposable on one another. And this matters a lot because it turns out that there are examples of pharmaceuticals where the left enantiomer, or mirror image, is in fact therapeutic, but if you take the right enantiomer, it's toxic. So one of the most interesting things about this project is that its importance derives from events that happened billions of years ago in the primordial soup when life on Earth was originating. It turns out that many of the molecules of which we are composed, so DNA, proteins, amino acids, sugars, are all chiral compounds. And in principle, you would expect to have 50% of the left-hand molecule and 50% of the right-hand molecule present. But it turns out that in life, those molecules only appear with one-handedness. So as an example, the DNA that we have, all right-handed DNA. All of the amino acids, they're left-handed amino acids. And this is why pharmaceutical purity matters. A left-handed molecule will interact differently with left-handed molecules in the body than the right-handed molecule would react. So this is part of a very interesting problem that people who are interested in the origins of life all think about. How, when, and why did all these molecules end up being enantiomerically pure with just one-handedness? So the problem that we're trying to work on is to understand how we might create these kinds of chiral molecules, but just create the particular handedness that is desirable. And in almost all situations, you want to prepare these compounds in such a way that you have the one with the desired properties. And this is a phenomenally difficult chemical synthesis, very difficult to do on a large scale as you might do in pharmaceutical production. And in fact, these types of syntheses contribute enormously to the cost of pharmaceuticals. So the idea is that if we can make chiral surfaces and just make one of the two hands of the surface, now we can conduct reactions on that surface in such a way that you just get the desired enantiomer. And the idea is that if we can do this, that this will support or make chiral drug synthesis much cheaper than it is today.